how's the problem set this week? I think it should hopefully be a little bit easier. The first problem, there is a trick, I realized, on the first problem. So have you guys managed to do the first problem?
I haven't looked at anything.
Okay. Isn't it due tomorrow? Okay, fine. I'm not gonna editorialize. Okay. Anyway, hopefully it's easier, but there is a little trick on the first problem that makes it very simple. Actually, after today's lecture, I think maybe you'll be able to figure out that trick on your own. Okay. Good. So far in this course, the sorts of observables that we've been computing have been the expectation values of field operators inserted at some locations, some points in space. And in some cases, these are the sorts of expectation values that we would be interested in computing. But if you're studying particle physics, then what you would really like to compute are really not things like endpoint functions, but really we would like to compute scattering amplitudes. So what do I mean by that? Well, let's imagine that you have some initial state where you have a bunch of particles. So let's imagine, say, you take a bunch of particles. Here, let me just start by drawing a picture, actually. So let's imagine that you take a bunch of particles, say 2 particles here, one with momentum p1 and another with momentum p2. Then something you might be interested in doing is studying some sort of process where these particles come in and then they undergo some sort of scattering and then some stuff comes out. These are the sorts of processes that you would study if you had some particle physics experiment or some nuclear physics experiment, or even in some cases some sort of condensed matter experiment. So what we would like to do is to compute the amplitude, the quantum mechanical amplitude, for some, say, n particle state. So let's say some initial state, we'll call it I, which would be an n particle state. So it would have particles of momentum p1 up to pn. So in the diagram that I showed you here, that was an example where n was equal to 2, where you have 2 incoming particles. And we would like to compute the amplitude for some n particle state to evolve into some, let's call it m particle state, which would be the final state of the scattering process, which would describe a bunch of particles with momenta q1 up to qm, where m was equal to 3 in the example that I just drew there. So to say that a little bit more formally, what we want to do is we want to figure out how we can compute the transition amplitude, where you start with some initial state I at time t equals minus infinity, and you end up with some final state f at some later time t equals to plus infinity. So this is the sort of thing that we might want to study if we were studying some scattering process. Now implicitly, I should make one comment here, which is that implicitly in this formula, I'm using the Schrodinger picture because I'm talking about states evolving in time. But usually in field theory, we actually work in the Heisenberg picture, where it's not the states that evolve in time, but rather operators that evolve in time. And so then we would write this just as the matrix element of some operator that we could call S. And it's this matrix S, or this operator S, that computes for us the amplitudes, or that encodes all of the amplitudes for different states to evolve into one another. And so this S is typically referred to as the S matrix. And to some extent, It is the basic object of interest if we're studying scattering theory in quantum field theory. S here stands for scattering, but usually people refer to it just as the S matrix rather than the scattering matrix. Okay. Now, if we were working in free quantum field theory, then this would be a reasonably straightforward task. We know what the Hilbert space of a free quantum field theory is. It's just the various different n particle states. And we know that these states are eigenstates of the Hamiltonian, so they don't evolve in time. So scattering in a free theory is completely trivial. S, if you like, is just the matrix which is proportional to the identity matrix. You know, if you start with some state and evolve for some time t, you'll just stay in that same state, at least if you work in an eigenbasis of the Hamiltonian, which of course the n particle states are. But what we're interested in doing is studying an interacting quantum field theory. And at first sight, we don't even really know how to precisely define these states in an interacting quantum field theory. You know, when we defined the n particle state in free quantum field theory, we began by writing down raising and lowering operators and checking that the Hamiltonian was essentially the Hamiltonian of a bunch of simple harmonic oscillators. But if you have an interacting theory, the Hamiltonian is not a bunch of simple harmonic oscillators. And so we don't know what the spectrum of the Hamiltonian even really looks like for an interacting field theory. So in an interacting field theory, I don't even really know how to define precisely these states that I've called, you know, I and F here, describing an n particle state or an m particle state. So in general, you know, the precise definition of what we would mean by, say, an n particle state in an interacting quantum field theory is actually something rather subtle. But the basic idea is that if we're only interested in computing scattering amplitudes, that is to say, we're only interested in studying states in the far past or the far future, then if you just look at this diagram that I've drawn here, you see we have some incoming particles with some momentum P1 and P2, but in the far past, those particles will be very widely separated. And likewise, in the far future, the three particles that I've written will be widely separated as well. And if you have some sort of interaction whose strength falls off with distance, then at very early or very late times, when the particles are widely separated, we can essentially ignore the interactions. So at early and late times, the particles are widely separated. So that means we can just ignore interactions. Now, what I'm not going to do is I'm not going to give you a proof of the fact that in some formal way for the path integral of quantum field theory, for example, we can prove that at early and late times we can really ignore the interactions between particles. To some extent, that's what the definition of a particle is. It's some sort of localized lump of energy which has the property that you can separate it infinitely far away from everything else in your theory. So to some extent, this idea is not really something we prove, but something that is really an axiom of quantum field theory, or part of our definition of what we mean by as a particle in quantum field theory. And sometimes this goes under the name of the cluster decomposition principle. So for example, if you look in Weinberg's book, or one of the more sort of systematic developments of quantum field theory, they'll start with cluster decomposition as an axiom rather than something you prove. And however, if we wanted to, and it turns out this is a rather lengthy proof, but if we wanted to, you could actually prove using sort of diagrammatic Feynman diagram techniques that, at least perturbatively, local quantum field theories of the sort that we're studying in this class do obey this cluster decomposition principle. But that's something that's a little outside of, it's a little too technical. So what I really want to do is just sort of propose as an axiom the idea that at early and late times, particles are widely separated. So we can apply the notions of free quantum field theory where the interactions go away, and then use this to understand how to compute these scattering amplitudes. Any questions on this before I continue? Can you hear me okay? I don't think I can really speak any louder than this. It is nice, it's sort of dramatic. Good. So what we want to do is consider some interacting quantum field theory. And what we want to do is we want to take our field operator phi, and what I would like to do is expand in Fourier coefficients, and we'll give names to these Fourier coefficients. We'll call them A and A dagger. But the crucial distinction between what I'm doing here and what I did in free field theory is that whereas in free field theory, the equations of motion told us that these A's were essentially time independent, they were just some operators. In an interacting quantum field theory, A and A dagger will depend on time in some way. This sort of reflects the fact that the definition of what you mean by a particle in an interacting quantum field theory is actually something rather subtle. So, for example, you could expand in terms of these positive and negative frequency wave functions, e to the ikx and e to the minus ikx, at some particular time t, but the expansion at some later time might be different, meaning that what you mean by a raising operator and a lowering operator would actually be a function of time. But the idea is that at early and late times, we can go ahead and construct the states in the Hilbert space just as we would in a free quantum field theory. So in particular, how would we write down, so let's say that we want to study some initial state where you have n particles with momenta p1 up to pn. How would you do that? Well, you would define that if we were in a free quantum field theory, we would just take a bunch of these raising operators and we would act them on the vacuum. And I've included here some normalization factors, which were just some sort of convention-dependent normalization factors that we introduced when we defined an n-particle state. And what I'm doing here is I'm really using the exact same definition of an n-particle state that I would in a free field theory, but I'm using the operators AP1, the operators AP dagger, defined at minus infinity as a way, at time equals minus infinity, as a way of defining my initial state. And similarly, if I have a final state where I have m particles with momenta q1 up to qn, then we would define that by using the raising operators at future infinity rather than past infinity. And sort of somewhat implicit in this notation is the idea that this vacuum state that I'm writing down here is annihilated by the lowering operators at plus or minus infinity. That's really the assumption that in the far past or the far future, when the particles are widely separated, I can essentially treat this thing as if it were a free quantum field theory. Okay? So that means if I wanted to go ahead and...
The first one is 2 over Q1, right? Of the F term.
Sorry, what was what's the question?
The first term of F is 2 over Q1, right? Not N.
Oh, sorry, Q1. Sorry about that. Good, thank you. So then our goal is to compute the amplitude for this initial state to evolve into the final state, which is just this, we just need to compute the overlap between the two states that I've written down above. So that's a bunch of normalization factors that I won't write down for you explicitly. You can just copy them down from above. But we would get, so we have to take the bra vector corresponding to F rather than the ket. So that'll turn those AQ daggers into AQs. And we get an expression which is very similar to the sort of expression that we would get if we were studying free quantum field theory. But the only difference is that the raising operators that we use for the initial state are defined in terms of the field at minus infinity, and the raising operators for the final state are defined in terms of the field at future infinity. So is everything clear so far? So I'm now going to use one of these sort of clever tricks, okay, that, you know, we all hate so much. Okay? And I'm not writing out those normalization factors explicitly, but I'll go ahead and write them down in a few minutes. What I would like to do is I would like to notice that the expression that I've written down here is time ordered. Remember that time ordering is the procedure where if you have an operator that involves the product of a bunch of local operators at some different times, say T1, T2, T3, and so forth, then the time ordering operator is just the one that moves all of the later operators to the left and the early operators to the right. And you can see that the expression that we've written down there is already time ordered. So I can write down that time ordering operator for free. And now I can do the following truly sneaky thing. I can add 0 to this expression in the following very clever way. Okay. So again, I'll just ignore that normalization factor. What I would like to do is that every time I have an AQ plus at time equals plus infinity, I want to subtract off an AQ at time equals minus infinity. So we get a product of the AQs at plus infinity minus the AQs at minus infinity. And similarly, every time I have an AP dagger at minus infinity, I'm going to subtract off the corresponding AP at time equals plus infinity. So at minus infinity minus APM dagger at time equals plus infinity. Okay. Now why can I do that? Well, I can do that because I have that time ordering symbol. What does that time ordering symbol do? So let's imagine that you have this term here, okay? When you time order it, that operator that's at t equals minus infinity, that gets moved all the way to the right, where it hits the vacuum. And remember, the vacuum is annihilated by all of the lowering operators. So that's just 0, that term there. And similarly, the extra term that I added here, that AP is defined at future infinity, at time t equals plus infinity. So that gets moved all the way to the left. And an A dagger annihilates the vacuum when acting on the bra vector from the right. That's just the definition of the vacuum. And so this is just a sort of dirty trick, a fancy way of writing 0. But we're going to use this in a second. And in fact, it's because of this dirty trick that, I mean, it's really because of this dirty trick that we consider time-ordered correlation functions from the beginning. I mean, you may wonder, so far we've seen that time-ordered correlation functions arose naturally from the path integral point of view. But we're also going to see here that it's really time-ordered correlation functions that arise when you want to extract scattering amplitudes from position space correlation functions. Okay, there's a question. Yes? Okay. There's a small subtlety here, which is that I'm assuming that all of the positions are distinct, so that all of the Q's are distinct from the P's, so that none of the Q's and P's are equal. If some of the Q's and P's are equal, then you'll get extra terms here that you have to take into account. So I'm just going to assume that, for the sake of argument, that all of the Q's and P's are distinct. Okay. If we wanted to go through that argument in a little more detail, we could. It's not something that I was planning on doing, because it just gets a little technical. But for example, if you look in your textbook, I'm sure that this is done. Great question. Any other questions?
What's happened to this S matrix?
Mm. So the S matrix, so S is really just the symbol that we use to denote the amplitude for some initial state to evolve into some final state. I mean, when I write, I'm really, yeah. Oops. Let's put it this way. Remember that in the Schrodinger picture, this S matrix is just the statement that you define some initial state at time t equals minus infinity and evolve it to some future state at time t equals plus infinity. So if you like, you could, yeah. Is that clear more or less? So if you like, I'm using Schrodinger picture here when I write down this operator. Yeah, so I don't actually, yeah. I mean, I'm literally just computing, so if you like, these are the Schrodinger picture states that I've written down here. And I'm just computing the overlap between the two. Good, okay. So now what I want to do is I want to figure out a way of relating this correlation function of a bunch of raising and lowering operators to a correlation function of some fields. So the expectation values of a product of a bunch of fields, the sort of stuff that we've been computing so far in this course. So in particular, the claim that I would like to make is that as an operator, if you think of the difference between, say, one of these lowering operators at future infinity and past infinity, that is actually just given by a very particular integral of our field operator. So the first comment that I'll make is that remember that A is linear, that phi is linear in A. So you would expect that this combination of A at plus infinity and A at minus infinity is given by something linear in phi. But what I've done here is I've written down the particular linear operator that you have to act on phi with in order to extract these particular combination of lowering operators. So let's just go ahead and verify this. So in particular, what I'd like to do is I'd like to go ahead and just compute this guy. So the first thing that I'll do is I'm going to separate out the time derivative from the spatial derivatives. And I'm going to assume that my field at fixed time falls off quickly, sufficiently quickly at spatial infinity that I can just integrate by parts so that the spatial derivatives just act on the e to the I qx here. So you get a dt squared plus q vector squared plus m squared times 5. So that's just integrating by parts twice and acting the spatial derivative on e to the I qx. And of course, this combination of q squared and m squared is what we call omega squared. And then what I want to do is I want to note that in fact this quantity that you've written here is actually a total time derivative. In particular, it's the time derivative of e to the I qx times I dt plus omega times phi. So let's just check that that's true very quickly. Well, there are actually 4 different terms that you need to check. So first of all, if you have the dt and this dt acting on phi, that gives you this dt squared right here. And you have the dt acting on phi times this omega, so you get an omega phi dot term. But if you act with d by dt on e to the I qx, what do you get? You get e to the I qx times I omega. So you'll get an I omega term where the d by dt acts on this guy and multiplies that id by dt term, so that'll give you a minus omega phi dot term. And finally, you'll get this omega term times this guy, which will give you this omega squared term that we're looking for up above. So we've noticed that this particular integral is a total time derivative. So that means that you can use the fundamental theorem of calculus to write this as the difference between the integral at plus infinity, or the integrand at plus infinity, and the integrand at minus infinity. So it's the integral d3x of e to the iqx of I d by dt plus omega acting on phi, all evaluated at t equals plus infinity, minus the same thing evaluated at t equals minus infinity. And so now what we can do is we can insert just the definition of phi again in terms of the raising and lowering operators. So what did we have? We had ak of t times e to the ikx, or maybe it was a minus ikx, I don't actually remember. E to the minus ikx plus the Hermitian conjugate So what happens when you insert that into this expression here? Well, the first thing that happens is that you can use the x integral to give you a delta function that sets q equals to k. And then you can use that delta function to do the k integral. And so what you get is just the integrand evaluated at k equals to q. And then we also need to take this differential operator and act it on phi. And so it has to act on this exponential here. And that's going to pick out this term, because this is the term where id by dt is equal to omega. And this is the term where id by dt is equal to minus omega. So when you act with that differential operator, it will turn this guy to 0, and it'll turn this guy into a 2 omega. So you get the square root of 2 omega times aq, well, at t equals plus infinity coming from the first term, and then minus the same thing at t equals minus infinity from the second term. Okay, so this was just a sort of mathematical proof. But if we put this all together, the result, so just to remind you of what we were doing, we were going ahead and we were computing this S matrix, the scattering amplitude, and we found that it was the time-ordered product of a bunch of differences of these raising and lowering operators at future and past infinity. And then we gave a simple expression here for how this is related to a field value, a field operator. And so what that means is that you're going to end up with an expression which relates the scattering amplitude to the correlation function of a bunch of field operators. Okay? We just plug that expression in, so we had an integral d4. So let's say, so we had incoming particles with momenta p1 up to pm, and outgoing particles with momenta q1 up to qm. So for each one of those incoming particles, we need to use this formula here. We actually need to use the Hermitian conjugate of it in order to get a daggers instead of a's. And so we need to introduce n x variables, one for each incoming particle. So you get an integral d for x1 times e to the minus I p1 x1, because we took the Hermitian conjugate of that differential operator, and you get one differential operator for each one of our incoming particles. And you also get one of these differential operators, so I'll call their locations y, for each one of the outgoing particles. And all of this acts on the time-ordered correlation function of a bunch of phi's. So it's, what do we call that? Y1 up to Ym. Okay. I mean, it's worth pausing for a second and sort of thinking about what we've done here. What we've done here is we've taken the observables that we've spent so much time computing so far in this course, namely the correlation functions of a bunch of the field operators, and turning that into an expression for the scattering amplitude. So this is the basic formula that relates these two different interesting observables in theory. It's known as the LSZ formula, or sometimes the LSZ formula. And it has a couple of properties that I think we should probably just mention. The first property is that if you wanted to study n to m point scattering, so that is to say you wanted to study a collection of n incoming particles and m outgoing particles, then that means that this is computed by an n plus m point function. So for example, if you wanted to study 2 to 2 scattering, then that's computed by looking at some 4-point function of the phi's. Or if you wanted to study 1 to 3 scattering, that's also computed by a 4-point function of the phi's. The second comment that I'll make is that if we were studying free fields, remember the free fields obey the Klein-Gordon equation. And so in this case, this S matrix is just completely trivial. In fact, you might be a little confused at this point because you would think that in a free field theory, the S matrix is not completely trivial, because if you start with some initial state, you should be able to end up in that same initial state. But in fact, and in order to see that from this formula, you need to take into account the subtlety that I neglected earlier when you asked your question, when you asked about whether I should worry about setting some of the initial momenta equal to the final momenta. Turns out if we worked out that subtlety where we set initial momenta equal to final momenta, you would reproduce precisely the sort of delta function that you would get in a free theory where you had the same initial particles going to the same final particles. Any questions on this before I continue? Okay. So let's just do a simple example just to kind of make sure that we understand exactly what's going on. And then I'll work out a slightly more sophisticated example later on in this class. So let's just do the very simple example of the computation of, say, the computation of a scattering amplitude. Well, not really a scattering amplitude, but we could call it a transition amplitude. We have an initial state, which is just a single particle with momentum p, and a final state, which is just a single particle with momentum q. And let's ask what the various contributions to the scattering amplitude would look like. So the first comment that we'll make is that this quantity, so what is that? So let's just plug in that formula here. So we get an integral d4x and an e to the minus I px dx squared plus m squared, and an integral d4y for the final particle times an e to the I qy times dy squared plus m squared. And all of that acts on the time-ordered expectation value of phi x, phi y. So that's our scattering amplitude. And what we can now do is use our Feynman rules to compute this two-point function perturbatively in our coupling constant. So just for example, I'm going to continue using the interacting field theory that we studied last class, which is phi cubed theory, where I remind you the two-point function would be computed by summing over Feynman diagrams where you include these trivalent vertices where three lines can come together and interact at the cost of introducing 1 power of the coupling constant. So the leading contribution is the one that would be present even when g equals 0, and that's just the free field theory computation. That is to say, the free field theory two-point function, which in the language of Feynman diagrams we would write like this. So remember that you get you have one dot for each external vertex, and this two dots connected by a line is just a notation for the Feynman propagator that describes the free field amplitude for this two-point function, phi of x, phi of y. So what was that thing? Let's just write it out explicitly. That was I times the integral d4k. I'm going to use the momentum space representation of this for reasons that will hopefully become clear shortly. So it's the integral d4k of I k x minus y divided by k squared minus m squared. That's just the statement that in momentum space, this propagator is 1 over k squared minus m squared, which you can think of as the inverse of the Klein-Gordon operator, which was k squared plus m squared, k squared minus m squared, or d by dx squared minus m squared. So let's just go ahead and plug that in. So this gives a contribution to the scattering amplitude. And what does that contribution look like? Well, we have an integral d4x, an integral d4y, and an integral d4k coming from the two-point function. And we get a bunch of exponentials. We get an exponential e to the minus ipx, e to the plus iqy, and from the Feynman propagator, an e to the ik x minus y. And then we get, well, we have that 1 over k squared minus m squared from the propagator. But you also have the d by dx squared acting on the propagator. So what does that give you? That gives you a k squared. That gives you, well, minus k squared plus m squared. And then you get another factor of minus k squared plus m squared coming from here. So you end up with a total factor of k squared minus m squared. So we had two factors in the numerator, one coming from each one of these derivatives, so that d by dx squared just hits this x here in the propagator, and it brings down ik squared, so minus k squared. And so this term here gave you a minus k squared plus m squared. That gave you another minus k squared plus m squared. You get a minus sign from those two factors, which cancels an I squared from here, and then you cancel one of the k squareds. K squared, that one of those gets canceled by that k squared minus m squared in the denominator. And so you can now just do that integral. So, for example, doing the x integral gives you a delta function that sets p equals to k, which you can use to do, and the y integral gives you a delta function that sets q equals to k. And so you can then just do the k integral to get rid of one of those delta functions. And what you get is q squared minus m squared times a delta function that sets p equals to q. So remember what we're computing here. What we're computing is the amplitude for some initial state with momentum p to evolve into some final state with momentum q. And the important term here, which is the one that I want to emphasize, is this delta function here. And that delta function says that the momentum of the initial state is the same as the momentum of the final state. So this is a momentum conserving delta function. And if we'd been clever and thought about it ahead of time, we could have immediately guessed that we would have gotten a delta function like this. Because no matter what you do in a field theory, as long as you have translation invariance so that momentum is conserved, then if you scatter a bunch of incoming particles with some total momentum together, then the end product should have a total momentum that equals that of the initial configuration. So what I'm now going to do, so far this was relatively simple. What I'm now going to do is do this procedure for a slightly more complicated contribution to this two-point function and use this to sort of understand how we develop the Feynman rules for computing these scattering amplitudes in momentum space. But before I do so, let me just pause and see if there are any questions. No questions? Everyone's sort of quiet today. Just because I'm losing my voice doesn't mean that you have to be quiet also. Okay. So let's consider another contribution. So let's consider a more sophisticated contribution. Okay. So let's consider instead a contribution from a more exotic Feynman diagram. So let's consider the contribution to, so what did I call them? 5x1 and 5x2. Oh shoot. I call them x and y here. You know what I'm going to do is I'm going to call them x1 and x2 because that's the notation that we used when we were studying position space Feynman diagrams earlier. So let's consider a contribution where you have one external state at position x1 and your other external state at position x2, and then in a phi cubed theory, you would get some Feynman diagram contribution that looks like this, where we have some vertex. So how would you tell the story of this Feynman diagram? You would say, well, you had a particle at x1 that propagated for a little while. Then at some other position x, it splits into two particles, which then recombine at a position y before moving to your final position x2. And the Feynman diagram gives you an instruction for computing the contribution to the two-point function from this process. So you get a g squared because you have two interaction vertices, each of which comes with a power of I times g. You have a 2 because the symmetry factor of the Feynman diagram is 2. You have to integrate over the positions of these internal vertices, and then you get a bunch of propagators. So using the notation we used last time, you get a propagator from point 1 to x, 2 propagators from x to y, and a propagator from y to 2. And so now what we just want to do is we want to use the expression that we developed earlier, or that we used earlier, for the propagator in momentum space. Excuse me. So what you get, well, so we have these integral d4x's and an integral d4y. And now what we want to do is we want to use the expression that we wrote down above for our propagator. So we want to use this expression here. Now we have 4 propagators, so we're going to get 4 different momentum. Okay? So what I'll do is I'll call these momenta d4k1, d4k2, d4k3, and d4k4. So you get those factors of 2 pi associated with each one of those momentum integrals. And what I'm going to do, so I'll just draw the diagram again to remind you of which propagator is which associated with which momentum. So we had a position x1 here, a position x2, that was your position x, and here's your position y. So I'll let k1 be the momentum associated with that propagator here, k2 be the momentum associated with that propagator there, and I'll let k3 and k4 be the momenta that we use to write down the two internal propagators. And so what is the integrand then? Well, you get an e to the I k1 times x1 minus x, and e to the I k2 times y minus x2. That's from this propagator and this propagator. And then you get an e to the I k3 times x minus y, and an e to the I k4 times x minus y. And then you get a denominator for each one of these, which is k squared minus m squared. So you get a k1 squared minus m squared, a k2 squared minus m squared, a k3 squared minus m squared, and a k4 squared minus m squared. And you also get a factor of I for each propagator, but I to the fourth is equal to 1, so we don't need to worry about that one. Okay, so now we just need to start doing these integrals. So the first thing that I want you to do is I want you to think about doing that x integral. So the x integral is e to the I x times k1, what is it, k1, okay. Let's see. I guess I have to decide how I'm orienting these. So the x integral, you know what I'll do is, just to make life simple, I'll write these as y minus x instead of x minus y, just because it'll make, so of course I can do that just by taking k3 to minus k3, or k4 to minus k4. I'm going to do that just because it'll make the diagram look a little simpler at the end of the day. It's just an overall choice of what my integration variable is. So the x integral then is an integral e to the I x times k1 minus k3 minus k4. So that x integral gives you a delta function that sets k1 equals to k3 plus k4. And similarly, the y integral is an integral e to the iy times k2 plus k3 plus k4. Shoot. Okay, sorry. Yeah, sorry. It's an e. Yeah, I guess I want to do that same change there, just to make everything look a little simpler. So it is x2 minus y. So that's going to give you a delta function. So it's an integral e to the iy times k3 plus k4 minus k2. So that'll give you a delta function of k3 plus k4 minus k2. So I want you to look at those delta functions for a second. So what do? The first one of those sets k1 equals to k3 plus k4. And if you look at this diagram right here, what does it mean to set k1 equals to k3 plus k4? Well, what you can do, let me just redraw that diagram a little bit bigger. You can think of the diagram as being associated with some particle with a momentum k1 that's propagating like this, that splits into two particles with momentum k3 and k4, which then recombine into some final particle with momentum k2. And these delta functions just enforce momentum conservation at each one of those vertices. So you see that the K that's appearing when we write down the momentum space representation of the two-point function can be interpreted literally as the momentum of a particle traveling from one point to another. And this interaction vertex has the property that it has to conserve momentum. So that if you have an interaction where one particle splits into two others, then the momentum of the first particle has to be the sum of the momenta of the two things it split into. Any questions on that? Great. Okay, so you can now use these to do one of the K integrals. Okay. So in particular, let's just rewrite this formula. So we've got a minus g squared over 2. We've now done the x and the y integrals. We have an integral d4k1 and an integral d4k2. I'm going to use one of those delta functions to do, say, the k4 integral. Okay. So we're left with an integral d4k3. Then so we've used that integral to do, we've used one of the delta functions to do the k4 integral. And you're left with one other integral. So let's say that we use this integral to do the k4. We use that delta function to do the k4 integral. So that means that you're left with this delta function, where you set k4 equals to k1 minus k3. So if you just plug that into this delta function here, what does it become? Well, it becomes a delta function that sets k1 equals to k2. Right. That's just the statement that if you preserve momentum at this delta function, and you preserve total momentum at that delta function, then the initial momentum k1 has to be equal to the final momentum k2. And you're left with a phase factor. Excuse me. You're left with a phase factor. What is the phase factor? You get an e to the I k1 x1 minus I, or let's see, I guess it's a plus I k2 x2, and then you had those denominators. So what were the denominators? Well, you had a k1 squared minus m squared, a k2 squared minus m squared, a k3 squared minus m squared, and then a k4 squared minus m squared. But we did the k4 integral using the delta function, and so k4 was equal to k1 minus k3. So you get k1 squared minus k3 squared minus m, sorry, k1 minus 3 squared minus m squared. And so this is the contribution to the two-point function coming from this particular Feynman diagram. Now we want to understand how to extract the scattering amplitude. So remember the scattering amplitude. What did we do? Well, you have to act with this differential operator, integral d4 x1 e to the minus I p1 x1 times d1 squared plus m squared. So x1 was the initial position of the particle, and then we have an integral d4 x2 times e to the plus I cube times x2 times d by d x2 squared plus m squared. And we have to act on it with this thing that we just wrote down up above. So previously, what I'd called x1 and x2, I'd called x and y here. So I'm just reusing this formula right here, except instead of what I called, so I called x and y the external positions here, and I've renamed them x1 and x2 in the computation below. Okay, great. So now this is pretty straightforward, because when you take this d1 squared plus m squared, you acted on that guy, you get a k1 squared. You get a minus k1 squared plus m squared, which cancels this denominator. When you take this operator, d2 squared plus m squared, you get a minus k2 squared plus m squared, which cancels that denominator. So you can see what's going on here, which is that in the LSZ formula, you had the differential operators, and all they're doing is they're killing the propagators that were connected to the external legs. So when you use these Feynman diagrams in momentum space, where at the end of the day, you're never going to need to include propagators associated with final legs, with external legs, precisely because these are the things that you get rid of when you want to compute a scattering amplitude. So now you just need to do the x1 and x2 integrals. So what is the x1 integral? Well, it's the integral of e to the I x1 times k1 minus p. So that's just a delta function that sets k1 equals to p. Similarly, the x2 integral is a delta function that sets k2 equals to q. So putting this all together, what do you get? You get minus g squared over 2 times a delta function, so this is just this delta function here, of p minus q. We got two delta functions of k1, and so the x1 integral gave a delta function that set k1 equal to p that we used to do the d4 k1, and similarly the x2 integral gives a delta function that sets k2 equals to q that we used to do this integral here, and you're just left with one integral d4 k3 of, so I guess there's some various factors of I that I haven't been very careful about, but you just get these two final terms here. You get a 1 over k3 squared minus m squared, and a 1 over k1 minus k3 squared minus m squared. But k1 is just the momentum of your initial particle. So what we end up with is a very simple expression for our scattering amplitude. So again, we get this delta function that sets p equals to q. So again, this is your momentum conserving delta function. And we get a contribution to this 2-point function, which has a sort of very nice story associated with it. So what is the story that you would tell yourself when you're writing down this Feynman diagram? Well, the story that you would tell yourself is that if you want to calculate the amplitude for a particle with momentum p to undergo a scattering process and end up as a particle with momentum q, well, what this diagram is doing is it's telling you that there's one contribution to that amplitude, which comes from this particle with momentum p splitting into two other particles, one of which has momentum k3, which we could just call k if we wanted to drop that 3 label, and the other of which, by momentum conservation, has momentum p minus k, so that their total momentum is conserved. And then they recombine and form some final particle. And because momentum is conserved at that final, at that second interaction vertex as well, in fact, this final momentum has to be equal to p as well. So hopefully what you can see here is that our position space Feynman rules for calculating correlation functions now translate into Feynman rules in momentum space for calculating scattering amplitudes. So the position space Feynman diagram, Feynman rules, give rules in momentum space for computing scattering amplitudes. And what those rules involve is they involve simply a momentum conserving delta function, a factor of the coupling constant for every interaction vertex, a factor of the propagator in momentum space for each propagator in this diagram, along with the statement that momentum is conserved when you write down this Feynman diagram, and finally an integral over this undetermined momentum that I called K in this diagram. So, are there any questions on that before we continue? So, in particular, what I'm going to do now is I'm just going to give you a sort of nice summary of what the Feynman rules are in momentum space. But before I do so, let me pause and see if there are any questions on that derivation. Okay. So maybe I can just summarize this. So here's the summary. If you've fallen asleep, now is a good time to wake up. Sorry, because I'm losing my voice, I can't actually say that particularly loudly. I sort of feel like because I'm losing my voice, I'm sort of putting everyone to sleep. So, I don't know, pinch yourselves or something like that. The statement is that this S matrix, what is it? Well, this S matrix always includes, so there's sort of a trivial piece that just tells you that there's some amplitude for particles to evolve into themselves. But it will always include a delta function that conserves momenta. So when we talk about scattering amplitudes, in order to prevent having to always write down these momentum conserving delta functions that say that the total number of incoming momenta is equal to the total number of outgoing momenta, we'll just define something that I'll call M, which is known as the scattering amplitude. So M is computed by summing over all diagrams with the property that they have one external line for each incoming or outgoing particle. And these lines will be labeled by the momentum of that particle, just as in this diagram that we wrote down above. The lines will be connected by vertices, and the exact form of the interaction vertices will depend on what sort of interactions you have in your theory. So for example, in a phi cubed theory, you have this vertex with 3 legs, which gives you a factor of I times G. Each internal lines each get a factor of the propagator in momentum space which is I, so each internal line gets a propagator in momentum space I over k squared minus m squared. External lines get no propagators. That actually makes the computation of Feynman diagrams in momentum space much simpler than the computation of Feynman diagrams in position space, because there's, generally speaking, a lot fewer propagators that you need to worry about. And the momenta of internal lines are determined by momentum conservation at each vertex. And finally, each undetermined momentum gets integrated over. And of course, we can't forget to divide by our friendly neighborhood symmetry factor. Okay. So that's it. These are the Feynman diagrams in momentum space. So really, this point forward in the course is going to, not entirely, but to a large extent, going to be a series of exercises in applying these rules to compute all sorts of interesting things.
Can you just scroll down?
Yes. So, starting next class, what I'll do is starting next class, what I think I'll probably do is we'll start discussing the actual computation of these Feynman diagrams. There are all sorts of subtleties involved in these Feynman diagram computations. We've spent a lot of time talking about generalities, but we actually have yet to compute one of these Feynman diagrams. And indeed, if you actually look at the integrals that arose in the Feynman diagram that I wrote down above, there actually are some sort of subtleties there that are important to discuss. For most of this semester, a lot of these subtleties are not going to be so important. And so we're going to focus on the sort of practical utility of these Feynman diagrams to compute things like scattering cross-sections, decay rates, before moving on to discuss some other sort of interesting aspects of particle physics. So for example, hopefully what we'll be able to do by the end of this semester is use these Feynman diagram techniques to compute the anomalous magnetic moment of the electron in quantum electrodynamics. Probably the most famous quantum field theory computation that there is, probably the most important. But really, at this point, you have the basic tool that you need to compute whatever you want in quantum field theory. So, of course, there's some subtleties. So far, I've introduced these Feynman diagrams in phi-cubed theory. Of course, we can generalize them in a kind of straightforward way to phi-4 theory, just you have a quartic interaction vertex instead of a cubic interaction vertex. Generalizing these to include spinors and fermions and photons is going to get a little bit more complicated. But you can already sort of guess how that's going to go. In particular, for example, if you imagined trying to study some scattering process where you send in a photon and you have it undergo some interaction process, then in addition to labeling the internal particle by the momentum of the photon, you'll also have to label it by the polarization of the photon. And so you'll compute a scattering amplitude not just as a function of the momenta of the incoming particles, but of their polarizations as well. And so there's a couple of little subtleties associated with that. But essentially the basic tool that you want in order to compute scattering amplitudes in quantum field theory is now, is now determined. So I should maybe make one comment, which is that I sort of appreciate that the derivation of these momentum space Feynman rules using the LSZ formula is a little technical, okay? you know, so it's like the derivation that I went through today is important, and I want you to understand it. But it's more important to understand the punchline. That is to say, to understand the momentum space Feynman rules that we're getting at the end of the day. So if you have questions on the LSE formula or on how I used it to derive this, that's great. But I really just want to make sure that you understand precisely these Feynman rules, because we're going to get a lot of practice using them. You're going to get a lot of practice using them in the problem sets. And so, you know, I want you to feel completely comfortable with that. I might make one sort of comment on how you should think about the various terms that appear in this Feynman diagram. Okay. So let's take this Feynman diagram that I've written here. Okay. You know, one of the things that you should keep in mind is that the picture that you have in your head, the story that you tell yourself when you write down this Feynman diagram, is that you have some incoming particle with momentum p that splits apart into two other particles of momentum k and p minus k. Now, you know that you're conserving momentum at this interaction vertex, but it's important to emphasize that the particles that are moving on these lines, they're not solving the equations of motion. Remember that particles that solve the equations of motion have k squared equals to m squared. These particles are not solving the equations of motion. And that's really a consequence, if you want to think about it that way, of the path integral formulation of quantum mechanics, where if you want to calculate the amplitude for some initial state to propagate to some final state, you have to sum over all possible paths that the particle could take, not just those that solve the equations of motion. So even though you conserve all of the various internal processes that occur in these Feynman diagrams, you conserve momentum, but you don't necessarily solve the equations of motion. And indeed, what is this integral d3k? You can think about this as a sum over all possible momenta that these virtual particles could take that are propagating around this loop in this Feynman diagram. So these particles that live on internal lines are often referred to as virtual particles. And when we do the sum over the momenta of all possible undetermined momenta in the Feynman diagram, we're summing over all possible momenta that these virtual particles could take. This is just like in a Feynman path integral where you sum over all possible paths that a particle could take. We're just doing it in a much more systematic way. Good. I guess that's all I have to say. Maybe I can pause here and see if there are any questions. In practice, I'll tell you that momentum space Feynman rules are much, much simpler than position space Feynman rules. So these things are actually much easier to calculate than the sorts of things that you would calculate if you were studying Feynman diagrams in position space. Any questions? Okay, good. I'll see you next week.